Hello, everybody. I am Flavio Souza from Brazil at ITA. I am a PhD candidate.
Hello, my name is Luiz Giacomossi. I'm a grad student at ITA, and in this video, we are going to present our paper entitled Autonomous and Collective Intelligence for UAV Swarm and Target Search Scenario.
This is the overview of our presentation. We begin with one introduction of context. In the sequence, we present the theoretical background related. Then we talk about the scenario of interest. Then we present the decision-making developed in this study. Thereby, we discuss the experiments and results of this work. And we finalize with a conclusion and future work. Swarm is a natural phenomenon of some groups of animals. Through simple rules, swarms entities manage the move in the space. The application of UAVs as swarm has been gaining attention and interest. However, this approach has many issues is open, with the capability to communicate between UAVs of swarm. The highest level of UAV swarm autonomy is the ability to perform a task coordinated among multiple UAVs without the intervention of a human operator. An important application is a search for targets that we cover in this work.
To model UAVs, we mainly apply two techniques. First, we introduce the steering force model. This method is used to guide the drone to a target by a simple sum of vectors, resulting in a vector force that is applied to the UAV model to guide this UAV to the target. We also have used the potential fields technique. It's a very traditional technique and used a simple variation using the equation of a normal bivariate function. A velocity field is created by taking the partial derivatives of this function, and then we can apply it as a collision avoidance method for the UAV. Using UAVs for search applications is not a new concept, but using several UAVs forming a swarm is still a not fully explored concept. Alnon and Cruz studied the usage of heuristic algorithms for search tasks using UAV swarms, and they concluded in their work that the search by line is the simplest and most efficient search method. This is the method that we are going to explore in our paper. Here the agents are going to be distributed by the lines of a discrete map, and they only progress by searching in not visited cells. We propose a scenario where a UAV swarm is applied in a search mission to find a missing individual. We assume that UAVs do not have previous information about the position of this individual. We also assume that the target is considered found when a UAV is in a range less than 20 meters of this target, considering that the UAVs are capable of identifying the target using a vision system. The last assumption is that the drones can communicate using a common network. So for this paper, we have developed a simulator to properly evaluate our methods. This simulator was developed in Python using the Pygame library. In this picture, you can see the simulator view. The UAV swarm is searching for the target, and there are obstacles in this scenario that UAVs must not collide. The decision-making that we developed in our paper can be divided in two categories: autonomous intelligence regarding a single autonomous UAV model, and a collective intelligence, since we are working with a group of drones. There are 6 models in total, 3 to each category. In autonomous intelligence, we have the target search model that is responsible to perform the search and selection of cells in a discrete map. The behavior model uses a state machine to control the autonomous behavior of a UAV. And a collision avoidance model is used to protect and preserve the agent. Now, as collective intelligence, we have the swarm search model that is responsible for mapping the regions that were not visited by the group in a discrete map. The blockage prevention model prevents the drones from getting stuck in regions of the scenario. This problem is common when using potential fields. Mission closure model: when a UAV finds the target, the coordinates are going to be shared to all the drones using the common network, so all UAVs can now move to this position. We have developed a state machine to control the autonomous behavior of the UAVs. This machine is seen in this figure. A copy of this machine is present in each drone. There are 4 behaviors: search target, seek state, go to the closest drone, and run on target. The default behavior is the search target. In this state, the UAV will perform the search for the individual. When the individual is found by a member of the swarm, the machine will transit to the seek state. Now the search stops. In this behavior, the UAV now knows the coordinates of the target and can go directly at him. There are 2 auxiliary states: go to the closest drone and run on target. Those behaviors implement the heuristics to avoid the blockage in local minima that are present in the potential fields technique. Now we are going to show a short presentation video of our simulator running. Note that the first iteration uses the target coordinates previously known to take this time as a reference for the best case scenario, so the swarm moves directly to the target. Also note that the cells that are being visited are marked. This map is updated at each time step and is shared by all drones. Here we can see how our blockage prevention heuristics work. The drone identifies that he's blocked. That is, he's not moving by a period of time. Then he will search in the UAV swarm network for the closest drone. He then will head to his coordinates and going to be set free. When all drones are finally within the radius marked around the target, the iteration is over, and a new one will begin with a different scenario, but maintaining the same number of agents. Now we will discuss the experiments and results obtained.
We apply a statistical evaluation, a complete factorial design. Consider the three factors, vary the numbers of drones and obstacles and search strategy. Pay attention to the first level of search strategy, when we use the target location previously known as the best case reference. It's important to say that the time complete of mission metrics is when our UAVs reach the target. Here we have the result of the mission completion time metrics. In most cases, the heuristics didn't present one influence on the performance of this metric, having as reference the values in the blue. We note that in all cases, the heuristic increased the completion time metrics. This behavior is expected. The heuristic method does not guarantee optional time. We also observe a big difference between 50 and 30 obstacles. With 15 obstacles, the time of mission is statistically bigger. This happened because we can have more difficult scenario with 15 obstacles than with 30 obstacles. Because the target can stay in region with very close obstacles, create big barriers. This graphic represents the quantity of the local minima in the experiments, again have as reference case in blue. We observe in our case that we used the heuristic there is a big reduction of the local minima. Remember that the local minima itself equals to the number of blocked UAVs during the experiments. This indicates a better efficiency in the search, with way less UAVs blocked.
In this work, we have studied how a swarm of UAVs can be used in search missions. A simulator was developed for this study. Using the simulator, we have studied intelligent search strategies using these autonomous UAVs. We have proposed heuristics to avoid the blockage of the agents when using potential fields. With our methods, we have seen that the swarm can be a very effective tool to search for mission targets. Future work should consider applying these techniques in a simulator, with a realistic physics for deeper evaluation. In our work, we have focused on the development of decision-making techniques, abstracting the evaluation with a more robust simulator. Future research should also analyze how optimization algorithms can improve these results, and can also apply reinforcement learn to learn more complex behaviors. These are the references of our work. Thank you so much for your attention.